Here we are going to calculate the adiabatic flame temperature for burning butane, normal butane, 100% excess air, and both the butane and the air enter at 25 degrees C. So given the heat capacity parameters, the heat capacity is form A plus B times T plus C times T squared plus D times T cubed. And what's important, and we want to keep in mind, these heat capacity parameters are only good over this temperature range. So if we end up calculating a temperature higher than 1800, it's not going to be a valid answer. We're going to have to go back and find different heat capacity values. So the reaction that we're interested in, normal butane, C4H10, and 13/2 oxygen gives us 4 CO2 and 5 water. Now, because we're going to use 100% excess air, that means if we have 1 mole of butane, we're going to have 13 over 2 times 2, 13 moles of O2 fed to the system. And then 13 times 79 over 21, which is 48.9 moles of nitrogen, where we're assuming air is 21% oxygen, 79% nitrogen. That's a reasonable approximation. So the way we're going to do the calculation, we're going to take advantage of this idea of state function, that we feed in 13O2, 48.9 moles of nitrogen, and 1 mole of C4H10, feeding them at 298 Kelvin. So we're going to visualize we carry out the reaction at 298 Kelvin, and the reason we do that is because now we can get the heat of reaction at 298 from heats of formation because we have tables at that temperature. What we're going to end up with then, we're going to have 4 moles of CO2, 5 moles of water. We're going to have unreacted oxygen, 6.5 moles. We had 100% excess. And of course, all the nitrogen is unreacted. So we're going to have that many moles of nitrogen. We're going to take then all of those species and heat them up to our flame temperature. And that means we're going to calculate this integral to go from 298 to the temperature we're trying to determine. And what we're going to write is the sum of the number of moles times the heat capacity of each of those species. So if we add these two together, that's the same as carrying out this reaction where delta H is equal to 0. So this is the adiabatic flame temperature, assume no heat loss. So let's first calculate the heat of reaction at 298, and the heat of reaction at 298 then is going to be 4 times the heat of formation of CO2, since it's 4 moles, 5 times heat of formation of water, minus the heat of formation of butane, minus 6.5 the heat of formation of O2. Of course, this is 0 because oxygen is an element. Now I can look up the values. Let me pause and write down these values I take from a table. So here's heat of reaction at 298. Then the other term, the heat capacity calculation, that's integral, 298 up to the flame temperature. The sum, number of moles, heat capacity dt, which I can write as the sum of Ni and then the heat capacity for each of the components, where this is Bi, Ci, and Di. So if I integrate that, I'm going to end up with the sum of Ni, Ai times T plus Bi, T squared over 2, Ci cubed over 3, and Dit to the 4th over 4. And then we have to apply the limits of integration. Well, I won't write out all these terms, but let me write out one just so we understand what we're talking about. The first one would be 4 times A for CO2 plus 5 times A for water plus 6.5 times A for oxygen plus 48.9 times A for nitrogen. And I apply the limits, it'd be T minus 298. I won't write the rest of the terms, but I've written B, so this would be the C terms and then the D terms. So then what we're doing is we're solving our equation, delta H for reaction at 298 plus this integral of the sum heat capacity terms from 298 to T equals to 0. And I'm going to use a spreadsheet because now we have a polynomial, temperatures unknown to 4th power. It's easiest to use solver in a spreadsheet. When I do that, I end up with adiabatic flame temperature 1510 Kelvin. Let me just show you the spreadsheet. So here we see I put in the heat capacity constants, the sum of the NI/AI terms, then the integral terms. Notice that the heat capacities are in joules per mole per Kelvin, heat reaction in kilojoules, so this sum I divided by 1,000 to put in the correct units. The spreadsheet's available at the LearnChemE.com site.